So we have a theoretical framework for discussing cosmology, and we will discuss the experiments that tell us how we know what we know about the structure of our universe in subsequent lectures. But let us pause for a moment to see how the principles, the ideas, these Friedmann equations and their solutions apply to telling the story of our universe. And in this clip, we'll tell the story of the past. We'll talk about the future in the next clip. So let us remind ourselves of the Friedmann equation. Here is Friedmann's equation. We wrote it here in the form that we saw it. So this is h of t squared is given by 8 pi g over 3 rho, where rho includes the energy density contributions of both dust and radiation. There is a curvature term, and there is this strange cosmological constant term. Remember that we are going to account for this by replacing it with an equivalent energy density. So rho lambda is set in such a way that 8 pi g over 3 rho lambda is lambda c squared over 3. This is just some constant term on the right-hand side of the equation. And we're going to rearrange the equation. So now, with rho, this folded into rho, the equation has three terms: rho, curvature, and h squared. We're going to move the curvature all by itself to one side, and then the rest of the equation is that this term is equal to h squared minus 8 pi g over 3 rho, and rho is the sum of three terms: dust, radiation, and cosmological term. And we're going to assume that these are conserved separately. We'll talk about that in a second. First, looking at this equation, it should appear very familiar. If you remember the equation for our Newtonian dust world, if the energy conservation equation we wrote then had this form, it had epsilon over a squared is h squared minus 8 pi g over 3 rho of t. So these equations are similar, very formally identical, in fact. The only question is that when we solved the equation, the solution we found had to do with the fact that we knew the A dependence of rho. We'll come back to that in a second. At the moment, the equations are formally identical if you identify epsilon with this number minus k r0 c squared, where remember r0 is the curvature of the universe at the present moment. And this suggests that we do the same kind of rescaling we did last time. There is a critical value of the density, the one that makes the right-hand side of the equation vanish. Then it was the distinguishing point between a universe that expanded forever and a universe that crunched back. Here, that's not quite the interpretation of the right-hand side. What the sign of this right-hand side determines is the sign of the left-hand side, which is the curvature of the universe. So if this term, if this whole combination here is positive, if H wins over the energy density, then K is negative, and the universe is hyperbolic. We have a negative curvature universe that is infinite and open. Whereas if the energy density is sufficiently large to overcome H, then we have a case of a positively curved universe, like the surface of a sphere, that is finite in extent. Whereas if this is 0, if h squared is equal to 8 pi g rho over 3, then the curvature of the universe is 0. This suggests that we scale rho by defining the same critical density we defined there. In terms of this, we define an object omega, in fact 3, omega dust, omega radiation, and omega lambda, each of which is the ratio of omega I to omega c at any time t. Remember, omega c, the critical density, is determined in terms of the Hubble constant at that time. And then, in terms of all of these notations, if we define omega as the sum of all three relative densities, then the Friedmann equation takes this rather beautiful, simple form. Cosmologists, which for years had very little data to work with, are great wizards and well known for repackaging equations in order to attempt to get insight from them. And this is certainly going to turn out to be a very useful way to write the Friedmann equation. Note that to determine the right-hand side, which is a constant, we can evaluate the left-hand side at any time. So we can measure the Hubble constant today. We know it. If we could measure omega, then we in particular would know the curvature of the universe. Now, as I mentioned before, we're going to assume that, modulo some caveats that I'll mention later, energy is conserved separately in the form of dust. Energy in radiation is separately conserved, what that means is that there are no large-scale conversions of one form to the other, no large-scale particle-antiparticle annihilation into radiation, for example, or no large-scale absorption. As long as that is true, then we know how these energy densities evolve with the expansion of the universe. We know, for example, that the energy density in dust is diluted as the universe expands by a factor of the scale factor to the -3. As the universe grows, matter is diluted. If all distances double, volumes are multiplied by 8. Since the mass of dust is conserved, what that means is that the mass density decreases by a factor of the volume. On the other hand, radiation density is diluted by the 4th power of the scale factor. The reason, of course, is that 3 of those factors have to do with the fact that the number density of photons, say, decreases as the 3rd power of A because the volume grows, and then the energy of each photon decreases by a factor of 8 because of the cosmological redshift. So radiation is diluted faster than dust. And then what about the cosmological term? Well, this is a constant. It has no A dependence and no T dependence. So the vacuum energy density, the cosmological term, is not diluted at all. If, as the universe doubles in size, the energy density in dark energy is constant. That's one of the weird properties of this object. We interpret it in some way as the energy density of the vacuum, I said. And if that's true, then it's clear that when the volume of the universe becomes larger, there's just more vacuum. And indeed, there is more vacuum energy. And so there is no dilution of the cosmological constant. Just this fact tells us something. It tells us that assuming that all 3 numbers are non-zero, no matter what their values, if you look far enough into the future, then as the universe expands, the dust component is diluted, the radiation component is diluted, but the cosmological term is not diluted. Far enough into the future, the cosmological term is much bigger than either the dust energy density or the radiation energy density, and the universe will be dominated by a cosmological term as long as it's not zero. Far enough into the past, on the other hand, as A of t becomes very small, the fastest growing term as A becomes small is the radiation energy density. Far enough into the past, that very small a, the universe, no matter where you start today, will be dominated by radiation, and this is going to form the guiding light for how we describe the evolution of our universe. So first, what do we know about our universe? Well, here is the data, and as I said, we'll discuss later how we know all these things, but these are the best known values, or some approximation to the currently known values of the energy densities scaled to today's critical density of about a 16th of a proton per cubic meter. And we said a little under 5% of the critical density is in the form of baryons, about 25% in the form of WIMPs or dark matter, a negligible fraction in the form of the cosmic microwave background. And so all of these we sort of discussed how we know them. What we have not discussed, and we will have to come back to, is how we know that the energy density in dark energy is about 74% of the critical density. We will find that out. The salient fact for us, of course, is that if you sum all of these together, you find that the total energy density scaled to the critical density is 1. In other words, it is an observational outcome of this that our universe is flat. Perhaps it is to the contrary. We measured that the universe is flat, knew these values, and concluded this from setting omega to 1, but we will discuss it. Given all this, we can go back to the Friedmann equation. We can cancel out, very happily, the curvature term. This is 0, and our equation becomes h squared times 1 minus omega equals 0, or if we remember that h is a dot over a, then this is a differential equation for a. The dependence of rho on a is given here. I give you these 3 numbers. They are given on the next slide, and you can just solve the equation. Now, the solution is not too complicated. It's simplest to solve the equation when there's only one kind of a dependence on the right-hand side. Then we can find simple equation solutions that are easy to write down. So we're going to pretend, just for simplicity, that at any given time, there's only one kind of energy density in the universe. In the deep future, it'll be all cosmological constant, and we'll set radiation and dust to 0. at intermediate times, it'll be all dust, and both radiation and cosmological term will be set to 0, and deep enough into the past, it'll be all radiation. None of this is precisely true, but it gives us the flavor of the solution. And so let's start by looking into the past. Currently, the cosmological term outmasses dust by a factor of about 3. That means that if you look into the past, remember that in the past dust was denser, but the cosmological constant hadn't changed. When the third power of the scale factor was 1/3 in the past, then the density of dust would have been equal to the density of energy in the form of dark energy, and before that, dust dominated dark energy, and it certainly dominated radiation. And so for the epoch in the history of the universe, until the scale factor hit the cube root of about a third, which is 0.7, which corresponds to a redshift. Remember, z is 1 over a minus 1 over 1, or 1 plus z is 1 over a. So that corresponds to a redshift of about 0.4. So distant objects, but we've seen pulsars way beyond that, and supernovae beyond that value of z. So we've seen into the matter-dominated era. And if you use our model, then T0, the current age of the universe, turns out to be 13.7 billion years rather than the 8 that we found in a purely dust-dominated universe. So this model describes our universe rather more consistently with the ages of clusters, and that's pleasing. And the time that corresponds to this value of A, we have a solution for A of t. We can figure out at what time after the Big Bang A was 0.7, and it turns out that about 8 billion years after the Big Bang is the time that cosmological dark energy density was the same as the energy density in terms of matter. If you look at it here, set about A of about 0.7 at about 8 billion years. And before this, the universe is effectively dominated by dust. And when the universe is dominated by dust, the Friedmann equation, we said, takes the form of the energy equation for dust world, and it's no coincidence that this graph should look familiar to you. It's nothing other than the epsilon equals 0 critical red graph that we drew in the process of dust world. In fact, the functional form of this graph is that A is proportional, here it is, to the 2/3 power of t, and then all of these factors are inserted to give it the right value at the boundary. So when t is equal to the time of the transition, it's equal to this value, because that's what we know it is. But A grows like the 2/3 power of t. This is a power less than 1, which means the expansion is slowing down, much as it did in dust world. And what that means is this generates a distant redshift relationship, just like the red one we drew for dust world. Remember, that deviated to the right of the Hubble law, which meant that distant galaxies showed redshifts in excess of what the Hubble law would predict. This had to do with the fact that in the past expansion was faster than it is in the present. So this is what we think describes the recent past of our universe. And this obtained up until an age of 8 billion years, so up until about 6 billion years ago, reasonably recently. And as we look back, of course, something interesting will happen in the dim, dark past, because far enough into the past, radiation will have dominated. Remember, in the past, we said radiation dominates. So somewhere at the beginning of this graph is an imprecision, which we will correct. But before we get there, there is one important event in the history of the universe that takes place somewhere in the beginning of this graph, but still within the dust-dominated epoch. And this is what is called last scattering. So let's understand what it is that I'm talking about. What do we need to remember? We need to remember that the past of the universe was denser, of course, density's scale. So when A was very small, the universe was a dense place. It was also hotter. Today's universe is relatively cool. The cosmic microwave background corresponds to about 3 degree Kelvin. But when A was very small, remember in the past, temperatures were higher. So at small values of A, we had high-frequency, short-wavelength photons filling the universe. And what this means is that when you go far enough into the past, hydrogen atoms could not exist. They could not exist because the photons that are now the cosmic microwave background had energies high enough, or ultraviolet photons with energies high enough to ionize hydrogen. Before that time, there were no hydrogen atoms. If an electron and a proton got together to form a hydrogen atom, a photon would come along and knock that electron out, and so hydrogen atoms were unstable to dissociation. After that time, the average wavelength of a photon became too long to ionize hydrogen, and then hydrogen atoms became stable. Now, this marks a watershed moment in the history of the universe. We call it the time of ionization, or sometimes rather paradoxically recombination, though recombination is a word borrowed from other contexts. In this context, the electrons and protons were not recombining, they were combining for essentially the very first time. Now, we can figure out what the temperature has to be for about half of the hydrogen atoms to be ionized, and that turns out to be on the order of 3,000 Kelvin. That obtained, therefore, when the redshift was about 1,000, so the scale factor was about 1,000th of its current value of 1. All distances were 1,000 times smaller than they are now. In our model, that occurred when the universe was about 380,000 years old, and something very important happened there. Because before this time, remember, the baryons in the universe consisted of a plasma, a dense plasma with a density of 10 to the 9, so 1 billion times denser than the quarter proton per cubic meter that we have now. And that plasma of charged particles was interacting, therefore, very strongly with the radiation field. Remember that in the sun, under similar conditions, a proton takes 100,000 years to penetrate the radiation zone, because a proton is absorbed and re-emitted and scattered mostly off of the free electrons in the plasma. So before the time of ionization, before this time 380,000 years after the Big Bang, photons didn't get very far. In fact, there was an efficient exchange of energy between dust or matter, baryonic matter in particular, and radiation, and the two were in equilibrium at the same temperature. Once hydrogen atoms formed, and the average photon no longer had enough energy to ionize hydrogen, then an interaction between the average hydrogen atom and an average photon resulted in nothing happening, unless the photon happened to be at precisely one of the resonant wavelengths of hydrogen. But most of the photons have just sailed through the universe unimpeded since then. So this last scattering surface is the time when radiation and matter decoupled, and since then, the energy in radiation has indeed been separately conserved, and the energy in matter has separately been conserved, or in dust has separately been conserved, and the two have become out of thermal equilibrium, and the temperature of matter, which is effectively 0 today, is not the same as the 3-degree temperature of the radiation field. More importantly, what happened to those photons after they scattered one last time off the last free electrons before ionization? Well, nothing. They've been soaring through a transparent universe, and these are the photons that we now observe as the cosmic microwave background. So we have a new interpretation of the cosmic microwave background. It is not necessary to go all the way back into the past to gamma rays emitted during fusion processes at 1 billion Kelvin. These photons were last interacting with matter. They last scattered at a temperature of 3,000 Kelvin, and since then have been traveling freely through the universe. So when we see the cosmic microwave background, we are seeing the universe as it was when it was a mere 380,000 years old, and farther into the universe we cannot see, because at previous times the universe was opaque, and any light that was produced prior to this last scattering scattered off of something. So the cosmic microwave background is literally the farthest thing we are able optically to see, not because of causality relations, but just because of the optical properties of the universe. This is a new perspective on the cosmic microwave background, to which we will return shortly. Now, moving farther back in time, we come to a time earlier than the time of ionization, or the surface of last scattering, during which, as predicted, radiation dominated. And so we can figure out when the energy density in radiation was equal to the energy density in dust, because we know their current values, and over time, one is amplified by a of t to the minus 4, one by a of t to the minus 3. The ratio is amplified by a of t. So we need A to B the inverse of the current ratio. In other words, radiation energy density was equal to dust energy density when distances in the universe were about 10,000th of their current value. This corresponds to a redshift value of about 3,300. Note, larger than the value at last scattering. So last scattering occurred during the matter-dominated era. In terms of time since the Big Bang, the model gives us 55,000 years. So hiding at the very bottom, much too small to see in this figure, of this graph of the dust-dominated era should be, in fact, a copy of this graph. Notice the scale here is tens of thousands of years rather than billions. And so this is a very small initial segment. And then what happens here is an interesting question to which we will return. So this is the early universe. Radiation-dominated universe is interesting. We should pause to ask ourselves, just what do we mean by radiation? Well, radiation is the way we describe all particles that move at relativistic speeds, whose pressures are non-trivial compared to their energy densities. And in a gas of particles, the average energy of a particle is k Boltzmann times T. And if the temperature is such that this is much larger than the rest energy of a particle, then that means that particle is moving at relativistic speeds. So as the temperature gets higher, particles of higher and higher mass will become relativistic. Of course, photons, which have zero mass, are always relativistic. Now, once we are at high enough temperature that some particle species becomes relativistic, then it just behaves almost like a gas of photons. Its energy spectrum is determined by, remember, the Planck law of black-body radiation is a property of thermodynamics. So the energy spectrum of a gas of electrons at very high energies is essentially described by the Planck spectrum. The average energy of a particle, of course, is on the order of kBt times 3/2 or some factor like of order 1. The energy density of a gas of relativistic particles at temperature T is given by an expression we've written down before. It's related, of course, to the Stefan-Boltzmann flux, sigma T to the fourth. We divided by a velocity for roughly the same reason that when we computed the number of WIMPs passing through every square meter, what we did is we took the number density of WIMPs and multiplied it by the velocity. Here, to get the energy density, we take the energy flux and divide by a velocity. And of course, the relevant velocity here is the speed of light. There's this factor of 4 that needs explanation. And then there's, for every species of particle, there is a geometric factor of order 1 that our dimensional analysis missed. It's called G. For photons, the value of the number G is 2. Essentially, this counts the number of states a photon of a given energy can have if it's moving in a particular direction. In the case of a photon, there are 2 separate polarization states. It can be right circularly polarized and left circular polarized. We haven't talked about polarization of light, so if that confuses you, just remember that G for a photon is 2. There may be other relativistic particles, depending on what temperature you're talking about, and at every temperature, we need to go through the list and figure out what's relativistic and account for its G. And then, when you have a relativistic gas, and the cosmic expansion redshifts the energies of the particles, because they are all described basically the same way as light is, the black-body spectrum is preserved, but the temperature declines like 1 power of the scale factor. Because, as you go into the past, the temperatures of the of any relativistic gas increases like 1 over A. If you go far enough into the past, you get to very high temperatures, and at suitably high temperatures, everything becomes relativistic. Deep in the past, in the early universe, there was no dust. All particle species were relativistic. This will become important soon.